Welcome to this video of axisymmetric stress analysis using finite element method. This video demonstrates how to use finite element method for solving axisymmetric problems. This video is intended for educational purpose. It will help students to understand application of finite element method for solving axisymmetric problems. It is expected that viewer is familiar with basic theory of finite element method and stress analysis using CST element. For matrix calculations, Scilab is used. In engineering, stress analysis problems, which involves analysis of three-dimensional axisymmetric solids or solids of revolutions, subjected to axisymmetric loading, are often analyzed as two-dimensional stress analysis problems. This considerably reduces the calculations needed for problem analysis, along with reasonably well accuracy of solution. Many examples can be quoted like a rotating flywheel, pipe carrying fluid under pressure, press fit of sleeve on a shaft. In this video, a problem of thick cylinder is taken for analysis of bursting forces. Forces similar to hoop stress. Consider the following problem, for analysis of the bursting stresses in the closed cylinder as shown in figure below. Figure A shows the cross-section of pipe. This cross-section when revolved around axis of symmetry, generates the three-dimensional pipe. Figure B shows the boundary conditions for the given problem. It is seen that, the edges AA and edge BB are, roller supported as shown in figure. Since we want tangential stresses, we will focus on section PQRS only. This section is highlighted by yellow rectangle as you can see here. Here attention is focused on section PQRS. Figure also shows edge BB, which is on horizontal axis of symmetry of pipe. Here, we will use CST element, for modeling the section to be analyzed. Since we have to find bursting or tangential stresses, we will only focus on section PQRS. Appropriate modeling of boundary conditions is necessary here. Here, we have divided the section in 4 CST elements, E1, E2, E3 and E4. It is quite obvious that, any triangle, when revolved around axis of symmetry, will generate a volume. Here, you can see the global node numbering for elements in figure A. The numbers in yellow ink are global node numbers. Figure B shows local node numbering specific to an element. Numbers in white ink are local node numbers. Note that, the element associativity table is very important as it will help to assemble global stiffness matrix K. The z-dimension of section is taken as 16 mm. Since, the boundary conditions and loading does not vary in z direction, the choice of z-dimension is arbitrarily taken here. Now, we will find strain displacement, B matrices for elements. The strain displacement matrix is 4 by 6 matrix here. Here, strain displacement, B1 matrix for element 1 is calculated. Here, strain displacement, B2 matrix for element 2 is calculated. Here, strain displacement, B3 matrix for element 3 is calculated. Here, strain displacement, B4 matrix for element 4 is calculated. You can see the relation between stress and strain here. S is stress vector. D is stress strain matrix. St is strain vector. Once B matrix is calculated, you can find local stiffness matrix, for every element using this relation. Here, stiffness matrix, K1 matrix for element 1 is calculated. Here, stiffness matrix, K2 matrix for element 2 is calculated. Here, stiffness matrix, K3 matrix for element 3 is calculated. Here, stiffness matrix, K4 matrix for element 4 is calculated. For complete section, global stiffness matrix is 10 by 10 matrix. As you can see that, internal pressure is a traction load. Therefore, the consistent loads acting at endpoint of edge 1, 2, can be easily obtained as shown here. Therefore, the global load vector can be formulated as shown here. Now our equilibrium equation is ready. It can be seen that, due to roller support on edge BB, the vertical movement of node 5 is blocked. Therefore, by elimination approach, we will cancel rows and columns corresponding to 10th degree of freedom. Upon solving the matrix equation, we get the nodal displacement values as shown here. It is interesting to note and compare the magnitudes and signs of nodal displacements. Just see the effect of symmetric boundary condition here. Here Q is nodal displacement vector specific to a given element. The values of stresses obtained denotes the intensity of stresses at centroid of CST element. It indicates that, if size of element is extremely small, you will get reasonably well accuracy of solution. This is called H formulation in finite element method. The column vectors S1, S2, S3, and S4 are stress vectors. The second row of S vector gives the magnitude of tangential stress. The equation A gives the tangential stress in thick cylinder subjected to internal pressure, Pi. Here, you can see the variation of tangential or bursting stresses along the radius, that is, across the thickness of pipe wall.